the title of my talk is to talk about continuous symmetries and hanging branes. And the reason why this would be what I will talk about, as you'll see, there will be a theme, at least today, about trying to understand continuous symmetries from this categorical and topological perspective, in particular how to talk about it from some bulk theory, which acts on some quantum field theory in some boundary. So one place where we can study such a question and try to understand in some detail is in holography, and in particular AdS CFT, where you have a concrete high-dimensional gravitational theory that is non-topological, that is dual to some field theory that we typically assign at the boundary of this thing. And the bulk gauge symmetries are going to be identified to boundary global symmetries. So there must be a procedure by which we can define an action of the symmetry from the bulk to the boundary. So this has been sort of fruitful in just understanding various categorical perspectives for finite symmetries that many of us here have worked on. So today, I will start to at least discuss some aspect how to do this for continuous symmetries, and in particular, in order to try to communicate some recent ideas and development, I will focus on a very specific setup where I want to discuss how to measure charge for n equal to 4 super Yang-Mills theory, which is dual to AdS5 times S5 here. And I'll try to be more concrete. So this is work based on collaboration with Federico, who's somewhere here, Enoch, who is looking for a job. You should hire him. He's great. And then a grad student of mine, Mufaro Chitoto. So this is from this paper, and there is some upcoming work. I should also mention that an important motivation for our work came from these two papers, which are two groups working in Ovidio and Teclion. Okay? So to start off, I will set up the problem, which is that why AdS CFT is interesting for this context is because when we think about AdS space, it's a space which has a boundary. It has a conformal boundary of sorts. So this would be the boundary of AdS here. And on the boundary, we like to think about the quantum field theory of interest as living there. It doesn't exactly live there, but there's a sense by which we can think about the quantum field theory lives there. So what you would like to know is the following. Is suppose for the quantum field theory, you insert some operator sitting here. So this operator is going to be under some representation R of some global symmetry G. And you would like to know how to measure the charge of this operator in your system. So of course, from a field theory point of view, what we would say is that you have some topological operator, which let's say I inserted in this way. So this is going to be on some domain M3, and we have some operator U, which depends on M3. And if it is for a continuous symmetry, then there are some continuous parameters that it depends on here, okay? And what you would like to know is how does the bulk theory give you a prescription for measuring the charge, and how does it give you a prescription for this operator that's sitting here, okay? So this has been successful in understanding many aspects for finite symmetries. So the way to approach this problem is basically when I insert an operator in the boundary of the theory, we usually think of this as having some Wilson line that's attached to it. So there is some Wilson line sitting here. Okay. Okay, I will not write with that one. So we want to understand, so to understand this problem is a combination. What happened? I don't have power for that. They do it. Can you switch off the lights above the boards? On. On, okay. I don't know. Okay, I will continue until they do so. Okay, so the point is, from a holographic point of view, right, the thing that gives you the Wilson line, which ends on the operator that you're interested in, should be some bulk extended object that live in the theory. And the thing that gives you the topological operator should also be some bulk thing that you should compute. And in particular, one of the things that we've understood more recently is that in the bulk, you have various Brane operators which are going to be extended by in some direction. And the particular thing you need to know here is the action of these branes typically will have some kinetic term plus some topological term. And what tend to be true by virtue of the geometry of AdS is as you take such a branes parallel to the boundary and near the boundary, the kinetic terms drop off, meaning those are going to be things that are suppressed. And the kinetic term is where the metric dependence comes from. And then you're left with something that is governed by some topological action. And in this way, in AdS CFT, you can recover topological operators. Okay? So we want to know how to build such a things in the case when I have a continuous symmetry. And the example we want to study here, and this is a good example for a couple of reasons. One, the theory in the boundary is n equal to 4 super Yang-Mills, and it has a global symmetry, which is an SO6 global symmetry. It's a non-abelian continuous symmetry. So that's nice. That's the example we want to understand. And then 2, it is also the canonical example for AdS CFT. And it's sort of funny, in the canonical model, this question has yet to be addressed in some way. Okay? So this is the one we want to study. And for what I will tell you, everything will generalize for other models of AdS CFT. And a lot of that appears in this second work that we have here. Okay? Any questions about motivation?
When you say it can be generalized, the bulk theory always have the same classical distribution?
Yes. So this is a case where we claim that we have some bulk supergravity, and then we can use that to try to understand the boundary symmetry. Yes.
Press to speak, yeah. So in this motivation where you said that the kinetic terms drop off, should we expect that that's only true sort of parametrically near the boundary? It's topological near the boundary,
yes.
But in the interior, the metric is still...
That's right. Okay. So I mean, to be more concrete to answer your question, the reason why that happens here is that the tension of the brane will scale us the AdS radius to some power. So then when you go, basically the excitations on the brane get very, very heavy. So you can decouple them systematically. Okay? Thank you for this question. Okay, good. So to set up this example, I will tell you about first this symmetry. And one way you can see this symmetry from the bulk is that we look at AdS space here, and then we have S5 sitting on top of it, and we can gauge the isometries of the sphere to give me some gauge theory that lives on AdS, okay? And the one way we do this is we turn on the SO5 gauge fields here, and then reduce the action with that, okay? And this whole geometry is going to be supported by a 5-form flux here, and this is going to play a role in various computations as we go. And this 5-form flux is going to be given by a global angular form on S5. And this goes back to an old story of Fried, Minassian, Moore, and where's the last author? Harvey. Okay. So this is the setup There are other fields that one could care about, but for the sake of understanding the topological structure, we don't need those fields. This will suffice. Okay. So the thing to first capture here is what is the effective theory that lives in the bulk. So we have some gauge theory, which I'll write as being given by minus 1 over 4 g squared. Okay, so you can take the supergravity action and then you reduce it onto this background. You get some gauge theory in AdS space, and this gauge theory is the one we want to study. And in particular, something that's going to be important is if we think about this gauge theory, there is a coupling here, which is a gauge coupling. This gauge coupling will have two sources. It has a source coming from reducing the Einstein-Hilbert term, and then it has a source coming from the flux. So this is a story that was worked out long ago by Ken and some collaborators. And this sort of the fact that you have these two sources is going to be an important hint on how to discover what the topological operators are. Okay, so I'll come back to this point. But before we try to understand what the operators should be from the full stringy point of view, you can think about this first at the low energy level here and ask, what do you get? Okay, so this theory, this gauge theory, is going to have some Gauss constraint in the bulk if I consider some, which is going to be the gauge derivative of FAB plus terms that involve the Chern-Simon kinetic, this Chern-Simon term in the action. And if I consider a Hamiltonian quantization of this theory, where I take the z direction as my time, okay, which is how we study this thing, at constant z slices, I need to impose this constraint on the state that when it acts on physical state is 0. Okay? And on states that are not physical, this Gauss constraint generates gauge transformation at constant slices. And the thing that happens when you take now this slice all the way to z equal to 0 at the boundary, at that slice, there is a Dirichlet boundary condition for the gauge field, which is this A at z equal to 0 is 0. And then at such a boundary, such a gauge transformation becomes global symmetry for the boundary modes that live there, right? In particular, it becomes the global symmetry, in this case, the SO6 global symmetry that would act on those local operators up there, okay? And the thing we want to know then are the symmetry operators that you can get for these SO6 global symmetry. Question? Okay. Okay, so that's statement 1. Statement 2 is, since at the boundary I have this Dirichlet boundary condition, the Gauss law simplifies. It simplifies to d star FAB is 0. And what this means now, this operator, at least from the low energy point of view, U of M3 on theta can be expressed as an exponential of I theta AB integral on N3 of this bulk operator that you have here, okay? So this gives you an actual, from the low energy limit, construction of this thing over 2g squared, which is important. Okay. Yep. So the SO6 is just a rotation of the sphere, and it's coming from here that you have. Okay, good. So from the low energy perspective, also, you have this Wilson line that you want to describe. Okay, so this is the Wilson line of SO6, which captures the representation for this operator here. And it is useful to describe this Wilson line slightly differently. So this Wilson line, we're going to describe it as an integral of some scalars, which I will tell you more about, minus of I, the action of the Wilson line. So if I consider this Wilson line, which is going to be a one-dimensional object here, I can write this action as a sigma model on this 1D object of this scalars chi which couples to the gauge field in the bulk. Okay, so here we have in mind that you pull the gauge field back onto the line, and then you have a scalar that lives there, and this scalar is going to be SO6 valued as given here. Okay, there's more to say here. So when we write the Wilson line in this way, there is a coefficient that I have to pick here, and this coefficient has information about the representation, and QAB is going to be an element of the dual algebra, in the dual algebra, SO6 star. And the choice of QAB is going to be equivalent to a choice of a representation associated to this thing. And the way you can see this is, first, if I integrate out the scalars chi, I recover the standard form of the Wilson line. But if I consider this scalar over here, we note that this action has several interesting symmetries. Okay? One, this scalar chi has a left symmetry action, where M is in SO6. So this is going to be canceled by the gauge transformation, which is M dm inverse plus M A M inverse. So that's just the fact that this, by construction, is to reproduce the Wilson line. But then there's also a gauge transformation that lives on the Wilson line itself, and this corresponds to a right action of this scalar chi here. So this right action does not act on A itself, but what it does is when you push it through, you find that it gives you a gauge transformation because the Wilson line action will change by a small amount, which is QAB H inverse DH. And of course, in order for this to be a gauge transformation, you want this to be an element of 2 pi z. Okay? So then this doesn't change the action at all. And what it tells you is that these coefficients Q, A, B here, so this is coupled with the constraint that H inverse Q, H is just Q. Okay? So this tells you that this action has a gauge symmetry that lives on it. And this gauge symmetry quantizes these charges here, okay? Which is something that you want. So actually, this gauge symmetry is going to be a set of, which we can define as SQ, is a set of element H in SO6 with this condition here. So the field chi, more specifically, becomes a map from M1 onto this co-adjoint orbits of Q, which is going to be SO6 mod SQ, which is a gauge transformation. Okay. So that's one symmetry that it has in the bulk. So this tells you actually this action as given, this is an action into the co-adjoint orbits of Q here. So you can use methods of co-adjoint orbits to quantize the theory, as you wish. So that's one statement. And then finally, you also have a global SO6 action that you can do to do a field redefinition. And what this allows you to do, then it tells you that you can always take QAB into the Cartan subalgebra. So you can pick only the following three choices to be non-zero, which is nice because then you can just pick these three charges, and then you can use the Weil group to move it into the fundamental chamber. So what these charges then become, they become the highest weights of the representation that you want, okay? So in this sense, you can see that if I study the Wilson line with this action, then this Wilson line exactly captures the representation of an operator that I would insert there. So when we say you want to measure the representation of this operator, it suffices to have a prescription that computes for you, that just picks out these highest weight states written in this way, okay? Good. So that's the Wilson line. So we have, from the low energy picture, the symmetry operator. The question now you want to ask is, how do these things get obtained from a top-down string theory perspective? Okay, so I will keep this here for now. Okay, first, let's see what is the origin of the Wilson line in the string theory. So the origin of the Wilson line in the string theory here is that you want to know which object in the string theory whose low energy limit has an action of this kind. Okay, so that's the analysis that you want to do. And it turns out the thing that you want to look at is a D3 brane in the full 10D string theory. And this D3 brane has to have a very specific shape in the sphere. So this D3 brane is going to be extended along M1 times some sigma 3, and sigma 3 is embedded inside the sphere. Okay? It turns out the correct object you want to take inside the sphere into this S5 is you can take the great sphere in the S5 here, which you can parameterize by some function ya times sigma I, where sigma I are coordinates, induced coordinates on the brane along the internal space. And once you have this gray sphere, for those who are familiar, this is a D brane corresponding to the giant graviton, but then is going to be Wick rotated along the AdS radius, for those who are familiar with that. So it turns out now, once you fix this shape of the D brane inside the sphere, you're allowed to actually spin it around. Okay? It can be spun around in a way that depends on the external space-time. So the actual shape of the D brane becomes ya of tau, where tau is a coordinate along M1, times sigma I, which is the coordinates in the sphere, times some map, which depends on tau, which is ya0 of sigma I. Okay? So in this very particular way, you see that once you fix the shape of the brane inside, it can then spin around inside the S5, and the mode that allows it to spin around is exactly this scalar that we have here. Go ahead.
But is the point that really what it does is it puffs up into this giant graviton?
Yes.
Great.
Yeah. So it's not, the excitation Yes, good. The excitation is not a KK mode. It's exactly the spinning of the brane. I mean, you can think of it as a KK mode. It's a flat direction because for what it is. So you can reduce now the action of the brane, okay? So you can reduce the action of the brane onto, with this specific choice, as an integral of m1 times sigma 3. And the relevant term that you care, because it turns out the leading term that you care about is coming from the coupling of the RR flux of this system, okay? So this would be coming from C4 inside. And then you can explicitly check that if you compute C4, you will get a term, you'll get the following term. You'll get chi inverse d chi plus chi a chi times some internal cycle, which I'll call omega, which is some three-dimensional thing. And this omega admit an expansion in terms of some choice of forms, omega AB, and these omega ABs have to be related to the sphere, and in particular, omega AB is obtained from the killing vectors of the sphere, which are given by YA, is it 2 dyb, okay? So the killing vectors of this space-time actually fixes the shape of this brane. So this is the quantity that you can get. And then you have choices of omega, where omega AB is just taking 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, just taking different great circles that you can take inside. And then you have a coefficient NAB, which pops out here, which is integral that you want to have, okay? And then when you plug everything into this action, you exactly recover what you want. There's usually an N, which is related to the AdS parameter, AB, times integral of the sigma model. So then you explicitly have, from this construction, that the embedding of the brane in the sphere is what generates for you exactly these charges that you will want to measure. Any questions? Mm-hmm. Yeah, I think the stabilizer is related to the thing that fixed Q, which is exactly the thing that I'm gauging, taking the modding by to get the coadjoint orbit.
Okay, apologies for not hitting the button.
Okay, so yes, good. That's a good question. So to answer, the stabilizer are going to be the thing that fixed QAB, which is exactly SQ up there. Okay, good. So the next object that you would like to understand before you do any measurements is then also the operator here, the symmetry operator here. So this object, it's a little bit more subtle how to get it, because naturally you expect to have just something that is extended on the boundary. But it turns out the correct thing that you would like to think about is not going to be just a line that is stuck in the boundary, and for reasons that I will explain in a moment, is that you can go back and ask from the reduction of the action, right? Remember we had the statement that you had the coupling that appeared in the gauge theory had two contributions. one coming from the Einstein-Hilbert term, and one coming from fluxes which are associated to the phi-form flux of the supergravity. So the fact that the gauge theory sector has two origins implies that the operator that you want will also have two origins. And in fact, what you conclude is that this term can be obtained by reducing what we call a KK monopole from the string theory setup, because the KK monopole is the thing that will source the metric. And then the flux term is obtained by reducing a D5 brane in coming from the string theory. Okay? So to understand T structures and how they emerge, let's first talk about this D5 brane. So to just tell you the dimensionality of this thing, the D5 brane has six extended legs. Similarly for the KK monopole, right? So you need to, in order for to have a D5 brane disk, you have an M3, but then you have to come up with the extra 3 directions somehow. Okay? So it turns out that the D5 brane is going to wrap some line, gamma 1, which I'll describe in a moment, times our desired M3 times some sigma 2, which this sigma 2 is a sigma 2 inside the sphere. Okay? So what is this configuration that it turns out to be? I will tell you what it is, and I'll explain later why we need to have it this way. So this configuration is the following, is that if I take my AdS boundary, what I can do is I can take the brane and then hang it onto the boundary here with some curve gamma. Okay, so this is a curve that starts and ends here. So this defines for me my gamma 1 there. And then there is M3, which goes inside the board in this way here. And then there is a sigma 2, which has to be inside the sphere. So when you have now the configuration of the brane in this way, you can check explicitly that when you study the action of the brane, right, and then you are integrating it on M3 times sigma 2, the correct thing that it couples to here for the fields of my theory is going to be a gauge field, A, which I'll describe, times the phi-form flux that we started here in the full background. A is a gauge field. It's a U1 gauge field that lives on the D5. And it is exactly the Chen-Patton gauge field on the D brane. Okay? And this configuration here, I mean, this is just by virtue of the action, so there is no control here. So the configuration of this gauge field is that A is flat. And in particular, it has support only on gamma 1. So integrating A on gamma 1 gives you some parameter alpha, where here the boundary condition is that A goes to 0 at boundary of gamma 1 in this open line. Okay? So this parameter alpha, you can then argue when you plug it back into the action, here you get integral of A G5 on gamma 1 times M3 times sigma 2, this is going to give you a coefficient alpha times integral of G5. And then this parameter alpha is going to be valued in R mod Z. Coming from the quantization condition of G5, you can also argue for this quantization in other ways. So then you can just evaluate the action exactly to what this is. And indeed, if you look at this G5, you have a piece which is in M3, and then you have a piece which is in the internal space. So this G5 is going to have a term which looks exactly FAB here times some I will put this as a omega 2, some 2 form. So this omega 2 could be expressed as coming from some coefficient MAB times D of KAB, where this was the killing vector that appeared up there. Go ahead.
Can I ask a clarification question?
Sure.
On the right part of the board, you have a symmetry defect operator that has support on one manifold M3 in the boundary.
Yeah.
And on the left part, we have two M3s because this gamma has two endpoints. Could
Good.
you clarify what's going on there?
Good. So there is an identification of these two in some way. When I do the integral, right, the two M3s are identified. They have the same exact data.
Okay, but should I think that this D5 brane on this manifold is producing one symmetry defect operator on M3?
It's producing one symmetry defect operator. And there is a neat way to understand why you need this. So maybe I come back to this question, because this is a useful point to explain. It's producing one symmetry defect. And the way you understand this opening here is that from the boundary theory, what you're doing, you're smearing the symmetry defect. Right? And this we know that you have to do, because if you try to insert exponential of the current with a delta function and you compute correlation functions, that delta function gives you singularity, so you have to regulate in some way. So the one way you can regulate is by smearing the insertion a little bit, compute correlation functions, and then take the smearing to 0. So this opening here precisely corresponds to this smearing or this regulator that you have to pick to compute correlation function in the field theory. Somehow, AdS CFT knew that you had to do this.
Another clarifying. Little a is the gauge field of G5.
Yes.
So G5, now you just said it has FAB in it. I thought F was the bulk gauge field.
Good. So F is a bulk gauge field in the AdS5.
That's right.
But G5 lives in the full 10D space where I have gauged all of the isometry directions. So when I compute G5, so earlier I said it was this global angular form, it is actually a very messy expression, which starts with the volume of the sphere and then lots of new terms, which depends on these gauge fields.
Okay, so that means that the form that you wrote there, A with G5, that's something that you are introducing to measure something, as opposed to that being some Vesuvino
So this is
term.
something that I did not fix by hand. The physics itself fixed it for you. So in the physics, to have this solution, there is a specific choice of a G5, which I didn't introduce. It just happens that if I look at the action of the D5, I have these Chern pattern fields, which could be turned on. And what this is telling me is that this Chern pattern field cannot be trivial. It's a flat connection, but I have to make a choice for it.
I guess what I'm asking, is that one of the Vesuvino terms coming
Yes,
from?
that's right. This is exactly the Vesuvino term that comes in, because the kinetic term. Actually, at this scale, because this is hanging brane, the kinetic term is important. It's because this brane is going inside. But one of the things that you can check is that even though this is hanging, when you compute the kinetic term, because this is a conformal brane that goes very far away, you could actually still exactly prove that if you pick a metric on M3, the dependence on the metric on M3 is going to drop off because of this hanging feature. So this is one of the reasons why the hanging brane seems to do the job quite nicely. And it indeed tells you, you can show exactly, it does not depend on the metric that you would pick in M3. So it has this topological nature to it. Any more questions? OK, excellent. So when you compute G5, you pick up this term that you want. And then you also pick up some 2 form that you have to pick. And this 2 form is exactly going to be given by this expression here. So here I can pause in a minute to explain what this is. So if I go inside the sphere and I make this choice of MAB times KAB, so this is a 1 form. So this 1 form defines for me, picks out a U1 here with some connection A. Let me put an A twiddle. And what it does, it splits the metric on the sphere as having a base, which is CP2 plus d psi plus A twiddle squared. I think there is a half in this definition. So you get a quarter. OK? So what is this two-dimensional submanifold? This two-dimensional submanifold corresponds to picking some U1 for the sphere. Then you have the base CP2, and then taking the 2 cycle in the base CP2, and that's where you wrap these 5 branes in the internal space. OK? And then you have a choice of that exactly given by MAB that sits here. So now when you compute the action of the D5 brane, you exactly recover the desired thing where you will have something that is n. You have these coefficients, MAB, times an integral of star FB exactly on M3 times the alpha sitting out here. And then there is a overall 1 over g squared, which is exactly the one coming from the flux. OK? So this action now reproduces the operator, at least a piece of the operator that you want for this D5. The second part that you also have to reproduce is the KK monopole term. And also for that one, there is a action for the KK monopole, which looks exactly like the Western term for the 5 brane, which is slightly different. In the following sense, if I look at now the KK monopole, I have an action where you have some 1 form times G5 for KK monopole. But V1 is not coming from a Chen pattern field. So V1 is coming from the fact that the KK monopole have 2 scalars that live on them, phi1 d phi2 minus phi2 d phi1. So the KK monopole of type 2b has 2 scalars that live on them, and these 2 combine to generate some U1 flat connection here. And then you have to make a choice. You have to turn on this quantity here. And indeed, you can then have integral of V1 on gamma to give you some alpha parameter in the KK monopole. Go ahead.
Can I ask what you mean by the KK monopole? Normally I think of KK monopole associated to a circle conductivity. Like the D6 brand that you made. What do you mean here?
Exactly associated to this circle. Yeah. So you can go ahead and compute it explicitly.
So the circle is some part of the S5.
Yeah. So you also have the KK monopole, which contributes alpha FK. The thing that we couldn't prove in our paper is that the contribution of alpha coming from the D5 and coming from the KK monopole are related by a factor of 2 in order to get the right result. So alpha from the D5 is equal to 2 alpha from KK. So we expect this is a property of the bound state that I need to understand to actually get this constraint, which is something that we don't do. So then in doing so, you recover a second contribution of that coupling, 1 over g squared, so I shouldn't actually, yeah. You recover the second contribution there, and then this second contribution put together gives you an operator that actually does reproduce the topological operator that you want in the boundary. Okay, any questions? Good, so now you have a picture, so let me just redraw it here, where we have our boundary AdS, we have some local operator sitting here, and this local operator can be described exactly by D3 brane with a choice of QAB that we introduced up there from two scalars. And then you have a D5 brane that is sitting here, which actually is not exactly a D5 brane, it's a hanging brane of this kind. So this would be the shape of the D5 sitting here. It's a D5 KK system, actually, not just a D5. So then you can ask now, how does charge measurement works, right? So charge measurement works by taking this operator and pushing it past the D3 brane, okay? And then ask, what do you get when you do that? Here I will draw some diagrams. So we redraw this, I'll put it this way. So you have a D3 that's coming down, and then you have a D5 that is sitting here. So when you pass this D5 KK system through, this is something you can explicitly compute in the string theory. You get back. It's hard to see the blue? Yeah, so I'll use the white. The white is fine then. You'll get the D3 back, as you expect. You have the D5 sitting here, but then you find that there is a residue that's inside. Okay? So when you just pass this through, you get a residue that's inside, and this residue here is going to be an F1 string that source the A gauge field. Okay? So you get the piece that you had before, which was the action of the D5 and the D3 before, and then the action of the D5 KK and the D3, but then you pick up a phase, and the phase that you pick up is coming from the action of the D3 brane, and the phase that you pick up is going to be exponential of I. There's an N coming from, just because you are in AdS CFT, times QAB times theta AB, which was the choice of the choice of your symmetry operator. So here now you explicitly see, so theta AB fixes symmetry operator. And then QAB fixes representation of operator, of boundary operator. Okay? And in doing so, you can explicitly now see that the bulk theory gives you a way of measuring the charge that you have in the boundary that you wanted to, that you started with. Okay, any questions?
I have a question. Can you say more about the configuration that's inside of the...
So this is a Hanani-Witten transition that occurs. because you have a D3 and a D5, which are codimension 2 between them. So when you pass the D3, you pick out an F1 that gets pulled. But because the D5 has this funny shape, the F1 that you pull, when it enters and it exits, it decouples from the D3, and it just becomes an F1 who's with a worldsheet F1 that's just hanging there. Yeah. So then you can compute the topological term associated with that. The other question you can ask about this is, in all of these manipulations, of course, here, I should be careful with what the kinetic terms are doing, okay? But the proper way to do it is you do holographic renormalization, you cut it off somewhere, you compute it, because the kinetic terms are blowing up, and then you normalize with the kinetic term, then take the limit as z going to 0, then you only pick up the topological terms of your system, okay, which is the thing to do. And indeed, this worldsheet of this fundamental string is large.
So can I ask a more basic question? So that as a first operator, you're talking about would include single trace operators that were studied very early on in computing.
Yeah. So in this case,
Saying that they actually have to be attached to these Wilson lines?
what I'm saying is that if I insert an operator in the boundary, I can consider it an endpoint of a Wilson line in the bulk.
But do I have to do that? If I want to insert that operator, is it necessarily attached to this Wilson line?
The way you should think about this is the HKL picture of where you have a bulk to boundaries. If I want to compute any correlation function that has this thing, I need to compute some bulk to boundary propagator, and that is exactly what this thing is, right? So this is a picture where I use to just to be able to measure what this charge is. Thank you for the question. Okay, so this picture, as described, seemed to do exactly what we want, and it shows that the bulk AdS CFT knows that there is a sort of topological prescription that allows you to measure charges for this field theory in the boundary. The next thing you would like to understand in the last 7 minutes that I have is what about fusion rules, and what about other properties that you might care about for this system. So without explaining too much, I'll just start drawing cartoons. So one thing you can try to compute explicitly from this string theory point of view is, suppose now I consider a system where, as I have described, that I have two operators here, two D5s, each one of them, this has some label of the group, theta AB1, and this has some other label, theta AB2, okay? And then I want to multiply the two and ask what I get. So it turns out when you try to do this, there's a more natural way to think about it, which is actually this hanging brane system, when you compute it, what you actually are doing, this is computed by taking a D5 brane that goes inside the bulk, and an anti-D5 brane that's sitting here, okay? So when you look at this system that is sitting at a finite distance, what you can see from the string theory is that there is a tachyon that lives here, and this tachyon becomes very strongly coupled as you go inside the bulk, and the tachyon coupling goes to 0 at the boundary, okay? So because the tachyon is becoming very strongly coupled in the bulk and is 0 at the boundary, what it does is that it eats up the D5 inside. And what this picture actually is, it corresponds to, when this dynamic settles, it basically corresponds to something that looks like a single D5, but actually is composed of two strands of a D5 and an anti-D5 with some orientation that you pick, okay? So what happens now when you then take these two things, what it turns out, when you bring them close together in the string theory, is that the two strands that are nearby, they want to annihilate each other, okay? And in fact, what happens when you bring the two is the two strands that are nearby, they annihilate each other, here, and they leave a residue there, which I'll tell you. And then there's a recombination that occurs inside that looks like that, where you get a D5 here and a D5 bar here. This object that's sitting here corresponds to a D4 brane in the type 2b picture, right? So D4 branes are unstable branes in type 2b. But if I put them at the boundary, the dynamics die so they can sit there. Then this D4 brane, you can then reopen this D4 brane because, so this is related to Clay's question earlier. So the reason why this opening here becomes non-physical, because this is secretly a D4 brane. So if I take the opening down to 0, it collides to a D4 brane that just sits at the boundary. Okay? So secretly this opening here that's why I call it a smearing. The physics does not depend on it because I can just close it and I get a D4 brane. So then this D4 brane can be opened up into a smaller D5, D5 bar, and then you have the outside D5, D5 bar. And then this picture is just now equivalent to two D5s that I put on top of each other. And then when I put the two D5s in each other, you can go ahead and compute and check that the theta will combine to give you the appropriate group element that you get for this combined system. Go ahead.
So this is very nice. It sounds very similar to actually something we studied in a paper this summer around sort of cylindrical configurations of branes. Can you check in this context that when you shrink the D5 with this holonomy, the tachyon field on the D4 is set to some particular value?
It has to.
It has to, right?
Because it has to give you the alpha parameter.
Fantastic.
Yes. And in fact, the thing that you can check is that here, the reason why you get a non-trivial flat connection, that flat connection is being Stuckelberged by the phase of the tachyon. Right? So that's why that A field is non-trivial. And that's why I can turn it on.
In that D4 picture, what is this suspended F1 string? Can you describe it?
Good. So this is the question he was just asking.
Oh, okay.
So in that D4, what you find is that there is some non-trivial phase that has to be, there's some non-trivial phase of the D4 that has to be there. And then that is the thing that reproduces the alpha parameter when you pass it through. So this is a statement that they have in their paper. And then from the D5, the correct thing to say is that when you look at this configuration, you are forced to turn on the Chen-Patton field. And the reason why you are forced to turn on the Chen-Patton field is when you study this tachyon condensation profile, the phase of the tachyon is non-trivial, but then you fix it but it couples to the gauge field on the D5, and then that is where it comes from, and that's where the alpha comes from, and that's when you take the limit for the D4, it gets reproduced there. So it's all consistent. Go ahead.
Quick comment is you could also think about these as flux branes, but this could possibly be some terminology difference. But
yes.
But also when you do this fusion in this tachyon condensation, I would expect you get like some non-invertible fusion rules. Do you have like a field theory interpretation of this SO6?
So in this setup, you don't. I mean, what you get is a non-commutativity.
Sure.
Right? Because of what you have. And then, and it turns out, if you work this out, so Enoch had a lot of fun doing these computations, is, you're using the Campbell-Baker-Hausdorff formula in various ways, so you can check that it works out. Okay. So your other question is now, suppose you have a symmetry that's so this is it's a non-abelian theory. What about if you have a symmetry that is non-invertible? From the bulk of the AdS, there isn't really any deep distinction about that, right? It's just going to be something you would compute in this process, and it would, if there's some non-invertibility, it would show up.
Thanks.
Okay. So my time is up, but so this is now to summarize. So this is a picture. This is where the hanging brain story comes from. There's a whole nother story I can tell you about how this dynamics works. But the upshot that I want to communicate is that the properties of symmetries can actually be computed directly from AdS CFT because it's something that we know is true, or we believe is true, and you can go ahead and check. And it's sort of impressive that just doing good old string theory computation can actually recover these features exactly, and it gives you an avenue to try to explore what these things should look like in general. So I'll stop here. Thank you.